So in the following examples, we're going to be classifying regions as being type 1, type 2, or potentially both. Now, associated with these, I'm going to recommend very strongly that as we're working on these problems, you start by actually sketching the region in question. Back in Calc 1, there was an entire unit dedicated to figuring out what the graphs of functions looks like. I'm not going to go that hardcore with you. I just want you to be able to come up with some decent looking graphs. So the first one shouldn't be too difficult for us to sketch. Now that I've said that, of course, I'm going to struggle with it. It is the triangle that is going to be comprised of the vertices 0, 0, 6, 0, and 0, 3. So the triangle in question, x-axis, y-axis, is going to connect 0, 0 with 6, 0 and connect that back to 0, 3. So the triangular region in question is going to look kind of like this. Here's our triangular region. Now at this point we have absolutely no functions that are actually up here, but two of them should be relatively easy to figure out. So two of the boundaries for the region will be the y-axis as well as the x-axis. The y-axis is defined as x is equal to 0, and the x-axis is defined as y equals 0. What we don't have is an equation for this line. Now, given 2 points that are on a line, I would certainly hope that you'd be able to come up with the equation of a line. We'll start with our typical y equals mx plus b kind of stuff. So the slope is going to be the change in y over the change in x. We'll say that we're moving from the point 0, 3 to the point 6, 0. Y decreases by 3, x increases by 6. The slope is going to be negative 1/2. Now with that in mind, we also have a y-intercept, so 3 will be our b value. So this would be y is equal to 1/2 x plus 3. We'll put that over here as well. In its current form, you have y defined as a function of x. As such, I would recommend that you go with a type 1 region for this. So in terms of a type 1 region, we have to say y is bounded below by a certain function and above by another function. Similar to what we did back in Calc 2, I would recommend that you draw yourself a little sample rectangle within here, going from top to bottom, and say what is our top boundary and what is our bottom boundary. You'll notice that the top boundary is the slanty line, and the bottom boundary, regardless of where we are in the region, is going to be the x-axis. So bounding below will be y equals 0. Bounding above will be this line. Then, once you have this in place, you say how far left and right will x go? Well, the farthest left that x goes is x equals 0, and the farthest right that it goes is x equals 6. So we'll say that x goes from 0 to 6. This would be the type 1 method for how to express this region. Now it is also possible that we could express this as a type 2 region, where instead of expressing y as a function of x, we can express x as a function of y, and say what bounds this thing left to right rather than top to bottom first. Now that would be putting bounds on x first. The left bound is going to be fairly straightforward to figure out because that's the y-axis, that's x equals 0. Whereas the right bound is going to be this slanty line. But for the slanty line, we would need this in the form x equals, not in the form y equals. Some quick algebra will let you know that if you solve this for x, you'll get x is equal to negative 2y plus 6. You can get that by multiplying both sides by 2, adding x, and subtracting 2y. So bounded on the left by x equals 0, bounded on the right by the line x equals negative 2y plus 6. Then y is going to be bounded from a constant to a constant. I see that bounding it below will be y equals 0, and bounding it above will be y equals 3. So we'll say that y goes from 0 to 3. Coolio. So this triangle is an example of a region that is easily expressible as both a type 1 region and a type 2 region. Now, which one you want to express it as is going to depend on the type of problem that we're dealing with, but we'll get into that more later. Next one. The region contained between y equals x squared minus 4 and y equals 4 minus x squared. you'll notice that in both of these cases, we're dealing with a parabola, and we're also dealing with y as a function of x. Because we're dealing with y as a function of x, I'm going to recommend that you go with a type 1 region for this. So first off, y equals x squared plus 4. That's a parabola whose vertex is at 0, -4, that opens in an upward direction, like so. Y equals 4 minus x squared is going to be a parabola with its vertex up at 0, 4. That's going to open in the downward direction. So the region in question would be this region right here. Now, if we are going to go type 1 with this, which is my recommendation, we would need to, once again, bound this thing from top to bottom, either with an arrow or a rectangle, whatever is easier for you to conceive. You'll notice that the upper bound for this region is the parabola that opens downward. So the upper bound is going to be the parabola that opens downward, whereas the lower boundary is the parabola that opens in the upward direction. So y is going to be between x squared minus 4 and 4 minus x squared. Then x is going to have to be in between two constants. Now, the way that I have it drawn here, it appears as though their points of intersection are actually the x-intercepts for this. That's merely coincidence on this one. Normally what you would do to come up with these points of intersection is set the two functions equal to each other. We can add x squared and subtract 4 from both sides, and then factor completely. Like I frequently say at parties when I'm invited to parties, a difference of perfect squares factors into binomial conjugates. Therefore, we're going to get that x is equal to either positive 2 or negative 2 from the two factors that we get here. So x is going to be bounded on the left by negative 2, and will be bounded on the right by positive 2. Now, if I wanted to express this as a type 2 region, let me explain why I definitely don't want to do that. First off, as we go from left to right, there are different functions that will define what is on the left and what is on the right. Up here, the right function would be the right half of the downward opening parabola, and the left bound would be the left half of the downward opening parabola. Those are going to result from, when we solve for x in this, we'll need plus or minus a square root. So I'm not saying it's not possible, I'm saying that you really don't want to because of the amount of work that it would take. This would actually have to be the union of two type 2 regions, or it can be one single type 1 region. If you're really interested in that, ask me about it during class and I'll show you how it's possible. There is one more that I wanted to talk about, and that is this one right here. The region that's contained by x equals y squared and x equals 3y. You'll notice that both of these are in the form x equals, and so you might find it advantageous to express this as a type 2 region. Regardless, I'd like to start by actually graphing this thing. X equals y squared will be the standard parabola, vertex at the origin opening to the right. X equals 3y is going to be a line like so. If we were to solve this for y, we would get a slope of 1/3, so not a whole lot of rise to the run. So here's our little sliver of a region that we see right here. Now I would like to start by expressing this in terms of a type 2 region, since we didn't get to do type 2 on the last one. For a type 2 region, once again, we'll be bounding this thing from left to right. We see that the function on the left is the parabola, whereas the function on the right is the straight line. So when we are bounding x in between these two functions of y, on the left we want the parabola. That's x equals y squared. And on the right we want the line. That's x equals 3y. Similar to what we did on our last example, if we're interested in the bounds for y, we can get those by setting these two functions equal to each other. So y squared is equal to 3y. Get a 0 on one side and factor the result. Lets us know that our two bounds on y are going to be y equals 0 and y equals 3. Now, if you wanted to be super thorough with this, what you could do is take y equals 0 and y equals 3 and plug them into each of these two functions and actually turn them into points of intersection. The reason that I bring that up is that it is possible to express this as a type 1 region due to the fact that it's only one top function and one bottom function all the way through here. So what you could do is say that going from top to bottom, the parabola is now the top function, the line is now the bottom function. But we don't have these in the proper form since they need to be in the form y equals. Solving each of these for y lets us know that the parabola is going to be y is equal to plus or minus the square root of x. You'll notice, though, that in the region in question, we're only dealing with the top half of the parabola. Therefore, we can stick with the positive square root of x. So as a type 1 region, the top function would be y is equal to the square root of x. The bottom function, once again, we would need to solve this for y. We would get y is equal to 1/3 x. That is the bottom function if we're going to express it as a type 1 region. Now, because we actually express them as ordered pairs, we can now safely say that x from left to right will go from 0 to 9. And that is how we would express this as a type 1 region. Again, there are going to be advantages and disadvantages to how you express it as either type 1 or type 2, or rather, why you would express it as type 1 or type 2. But we'll get into that once we actually do some examples.